Currently, the global system has been hit with a large force, that force being an exponential increase in CO2 in the atmosphere. Globally, our system is at an imbalance, causing a large disruption. We have dropped a large rock into the pond, and the ripple effect is in action. History shows that for 800,000 years, the Earth's atmosphere was in a balance of CO2 levels. According to NASA, CO2 in the atmosphere has increased from 280 parts per million to 408 parts per million. That is a 37% increase in CO2 levels since the Industrial Revolution.
All greenhouse gas concentrations have been rising. However, CO2 has one of the largest effects on global warming, as it remains in our atmosphere the longest. CO2 is an insulating gas, as it traps infrared heat from the sun. Approximately 56% of the CO2 emitted is absorbed by biomass and oceans, while the remaining 44% remains in the atmosphere. Yearly emission rates are expected to rise by 85% by 2100 as energy demand increases, while CO2 absorbed by oceans and biomass are expected to decline due to saturation and land use change.
Software simulations show an average increase of global temperatures of 3 degrees in 2100 if emissions continue on their path. The last ice age of the Earth was 2,000 years ago, with an average temperature difference of 6 to 9 degrees.
Climate modeling shows 3 degrees of surface temperature warming on average, with significantly more warming occurring at higher latitudes. The modeling suggests that warming could reach 8 degrees of warming in areas such as the Arctic Circle. Because sea ice is bright and reflective, the more ice that melts, the less sunlight is reflected back into space, causing temperature to rise faster. Global recognition of climate change has brought nations together to create the Paris Agreement. It was developed by participating countries and defined carbon emission targets. The goal of the Paris Agreement is to keep average surface warming to well below 2 degrees by 2100. As of 2016, we're currently off track, and our 1.5 degree warming target has currently a 50 to 66% probability of success. Current policy trajectory shows that actions need to be taken fast if we want this curve to trend downwards to even have a chance at 2% warming. The green area shows the amount of CO2 that must be captured. There are 3 strategies that can be done to mitigate emission: reduction of emissions, decarbonizing energy, and capturing carbon. Reducing demand is not likely to happen as it requires social and cultural change, which is much too slow to meet warming targets. Switching to less carbon-intensive fuels and using more renewable energy creates new problems. Power generation from renewables isn't reliable and would still require fossil fuels to meet energy demands. Many organizations and governments see carbon capture as a necessary technology to reduce emissions. Capture of carbon dioxide can be used on large, single-source CO2 emitters, such as power plants. The CO2 is filtered from the exhaust of these sources and compressed, transported, and then stored. There are 3 main types of carbon capture today. Post-combustion: the exhaust stream is separated into flue and CO2 streams, and then CO2 is absorbed by chemical absorbers. This technology is already being used for natural gas processing. For pre-combustion, the fuel is processed in a reactor with steam and air to produce a mixture of CO2 and hydrogen. Additional hydrogen and CO2 are produced by reacting carbon monoxide with steam. This mixture is then separated into CO2 and hydrogen. With the oxy-fuel process, fuel is processed using oxygen instead of air. This produces a purer stream of CO2. The mass and volume of the flue gas are reduced by approximately 75%, and the flue gas is primarily CO2 in high concentration. Net captured CO2 is approximately 80 to 90% of the exhaust streams. The extra energy requirements for CO2 capture is between 10 and 40% more. The choice of which technology to use is based on the process conditions under which the power production occurs. What do we do once we have captured CO2? We store it underground. After CO2 is captured, it can be transported by pipelines and taken to a storage facility. CO2 transportation in pipelines is already performed in the natural gas industry. On smaller scales, it is possible to transport CO2 by rail or road. In the USA, over 2,500 kilometers of pipelines transport more than 40 million tons of CO2 per year. Carbon needs to be stored responsibly. Several technologies that have been developed by the oil and gas industry provide the ability to store CO2. CO2 can be stored in deep onshore or offshore geological formations. At depth of 800 meters or more, CO2 becomes supercritical and has a density similar to liquid, which increases storage security and prevents CO2 from migrating towards the surface. Additionally, injecting CO2 beneath a caprock layer provides a physical barrier. Matches between large CO2 point sources and suitable geological storage formations is limited. Given expected technical limitations, around 20 to 40% of global fossil fuel CO2 emissions could be technically suitable for capture, including 30 to 60% of CO2 emissions from electricity generation and 30 to 40% of those from industry. Emissions from large-scale biomass conversion facilities could also be technically suitable for capture. In order to reach warming of 1.5 degrees by the end of the century, 675 gigatons of CO2 must be captured. This is equivalent to capturing approximately 19% of emissions from now until 2100.